Okay, let me briefly introduce the equation for lab 3 pipe metering. Okay, so let's start from the Venturi meter. Okay, as you remember, we have two tabs connected with the vinyl tubes to measure the pressure difference, right? So the continuity equation and the energy equation can be established, for these two cross sections. Okay, so A1 is a cross section of the pipe, and A2 is the area, cross section area for the the construction area. Okay, which is given. Okay, the construction diameter is 0.75 inches. Okay, so with these two equations, we are able to, using the equation 3.1, we are able to substitute the V1 with the velocity, with the V2, okay? So the equation can be rewrite as this: V2 equals to square root 2 delta P over rho 1 minus R squared. So the R is the ratio of the two cross-section area. Okay, the delta P is the P1 minus P2, is the pressure difference between these two tabs. And it can be calculated using the equation 3.4. So delta P equals to delta H times gamma M and gamma water. Okay, so that's the specific weight of the manometer fluid minus the specific weight of water. And the delta H is the reading you get from the manometer fluid. That's the difference of the manometer fluid surface level. Okay, so because it's a U-tube, right? You remember the manometer is a U-tube. So let me write, like this is a U-tube, right? So if there is a pressure difference in the pipe, so the surface elevation will not be normal, right? So at the beginning, the surface level of the manometer fluid should be level, but if there is a pressure change, so it could be like this, okay? So there is a surface elevation difference. So that's our delta H. And this information is given. It's in the data sheet. Delta H is given in the data sheet. So you're able to calculate the delta P using delta H, okay? And R is known, right? The density is known, so you're able to calculate the V2. So after we get the V2, we're able to calculate the discharge by just simply times the cross-section area, okay? Then the equation will be like this. And till now, we didn't consider any energy loss in the Venturi section. Therefore, we introduce a new term we call the discharge correction coefficient, CD. We just put it before the equation. So that's something we're going to use in the data analysis. Okay, so we just add the CD into this equation. It becomes our equation for the discharge. That's for the Venturi part. Okay, And for the orifice meter, the idea, the methodology is about the same. And we start from the continuity equation and the energy equation. So the only difference is the orifice plate, okay, create a we call it vena contracta, okay. So it causes the flow, cause a contraction for the flow, but we don't know what is the narrowest cross section, okay. By now, the only thing we know is the opening of the orifice plate. Okay, so for the continuity equation, the A2, V2, we don't know. We don't know the A2 right now, but we introduce a new term called CC. So we use CC times A equals to A2, okay? So we just substitute A2 with a new coefficient CC and A. So we're able to calculate the CC later. Okay, so the equation will like this, 3.14, and also we introduce the CD in here. Okay, so that's pretty much the same. Just the R is a little bit different. Okay, because R included CC here. Let me see. Okay, so from this equation, we introduce a new flow coefficient because that's too complicated. So we just want to use one coefficient K. So this K includes CD, CC, and also this part. Okay, so we take this part outside. So it will be square root 1 over R. And because the R has a CC inside, okay, so we take the CC out because R, we have the CC inside, R equal to CC A over A1, okay. So we just take the CC out and introduce a new term, beta. Beta equals to A over A1, okay. So in this term, the only thing we know is A and A1. The rest of the CD we don't know, CC we don't know by now. But so finally we will get an equation for the orifice. Okay, the equation will be Q equals to K times A. A is the opening of the orifice. Times square root 2 delta P over beta. Over rho. So the equation become pretty neat right now, right? So let's start with the data analysis. Okay. So the part 1, using the measured geometry pressure drop delta P and the flow rate Q equals to Q measure, calculate the following: CD and K. Okay. And do this for both CD and K using two following method. Okay, so the CD is for the Venturi section and the K is for the orifice. You see here, K, that's the equation for the orifice, and the rest of the equation is what we know. The Q is what we measured, A is known, and delta P is what we measure. So the only unknown in this equation is K. So we want to calculate K in here. And for the Venturi, as you can see, the only unknown in this equation is a CD, right? Delta P and Q is what we measured. A2 is known, and this part is known too, okay? So let me talk a little bit about the method one, okay? So for the method one, we create a variable x, a big X, equals to a square root 2 delta P over rho, okay? So the example in this menu is only for the orifice. So the equation for the Venturi section, you have to derive the equation by yourself. So I will only talk a little bit about the example in here. And for the orifice, let's see the equation right now. Okay. So basically it asks is you want to use this part as your variable x, okay? And your discharge, your measured discharge is your y, okay? And using the data, we can do another scatter plot, okay? But because we have a lot of delta P and we have a lot of a corresponding measured Q. So your and the K here, okay, it looks like a linear, right? It's a function of a straight line, right? So if you have your x, you can calculate something like that. Okay, that's your Q. The y-axis is your Q. The x-axis is this. And using the function, you will get a trend line in Excel. And I think you guys are pretty familiarized with this one because we use it a lot. I mean, in lab 1 and lab 2, just get a trend line, get an equation for the trend line, and the equation should be look like this: ax plus b. Okay. So what is a k in here? Because there is no intercept in this equation, so we have to force this line go back to the origin, which is 0. So there's no intercept in this equation. We want an equation, we want a fitted equation look like this: y equals to ax, and your a here, which is provided in the trend line equation in Excel. You can get it. So a equal to k in this case. Okay. So that's how we get the k. The k is your regression line, the slope of your regression line. Okay. Okay. So create a variable x and plot q versus x. That's what I was talking about. You have a scatter plot. Y-axis is q, x-axis is your x. Okay. Use the least square regression to fit a trend line to the data form y equals mx plus b, force the intercept b go to 0. So that's y equals to mx. Okay, so the slope you have is your coefficient k for the orifice. Okay, that's method 1. And method 2 is a little bit different. Okay, so we actually generalize the equation q equals to ka square root 2 delta p over rho as an n. So actually the n in our original equation is 0.5. Okay, so actually we introduce this n into this equation. Just substitute this 0.5. Okay, just substitute this square root. So this part will have a power of n. Okay. So what we're gonna do is we take a natural log, okay, of this equation. So the equation will become log q equals to n log delta p and blah blah blah. A lot of this. So just you probably notice the log q and log delta p are linear related. Why? Because if you treat this as an x, you treat log q as a y. Okay, so what does it looks pretty familiar, right? So your n is the slope of a straight line, and all these are your b intercept. Why? Because everything in here is a constant. Okay, your density is constant, slope constant, your k is constant, and your area is also constant. So the part A lets you plot log q versus log delta p. Okay, it should plot as a straight line. Okay, so for the second part, also we use a least square regression to fit a regression line in form of y equals to mx plus b. So this time we do not force the intercept into 0. Okay, that's because we need the intercept, because in the equation we already alter this equation to this, and it has an intercept to b. Okay, what it looks like is log q, okay, natural log q and natural log sorry, that's not correct. Natural log q is your y-axis, and natural log p is x-axis. Okay, so we just do the plot, and we will have a regression line like this, and this is our b. Okay, if there is a function for the regression line, it will be mx plus b. Okay, so what is b? B is this part. So once you get the equation for the regression line, your b will become like this. Okay, so b is from Excel. You will get the b from the Excel, and n is the slope. Okay, so n is the slope in here. You can also get it from, so the n is equal to m in here. Okay, so b and n is what we get from the trend line equation. Natural log 2 rho k and a. So the only unknown in here is a k. Okay, that's what we want. We want the coefficient, right? So we take the log k to the left-hand side, and the equation will be like this. And k can be calculated using the equation 3.23. Okay. So now you're able to calculate the k for the orifice. Use method 2. Okay. And let me just talk a little bit about the Venturi. Okay, I'm just I just want let's see. Okay, I think method 1 is straightforward. Okay, I think method 1 is straightforward because in the orifice you use this part as your x and this q as your y, right? But for the Venturi, it's a little bit different because the equation is different. So for the Venturi, it's actually this part as your x and your q as your y. And your CD is actually the slope, okay? If you draw the scatter plot or something. So the slope is your CD, okay? Once you get the figure, you get the trend line, you're able to get the CD. I think this part is straightforward, but for the second part, let's see. For the second part, it's a little bit different. So if you remember, the Venturi is Q equal to CD A2, right? Times 2 delta P. 2 delta P over 1 over R squared. I don't remember if it's correct. Okay, there's a row in here for the Venturi. CDA2, okay, row. Okay, there's a row in here. So if we want to generalize this, so we take the square root out, okay? Use an n instead. So see, be sure to start with q equals to CDA2 2p delta p over this to the power of n for the Venturi analysis rather than the orifice. Okay, so we start from here. Okay, we take a natural log for this. So what will be the result? So on the left hand side is natural log q, no problem. Okay, so this one, it will become n natural log 2 delta p over rho 1 minus r squared, right? And what is this part? Plus log CD plus log A2, right? It's pretty familiar, right? So we want to isolate this delta P out. So the right side, we can rewrite it. So it will be n log delta P, okay, plus n 2 over 1 r squared natural log, okay, plus log CD plus log A2. Okay, so that's the equation will look like. Sorry. Actually, okay. So there's a little bit different from the orifice, okay? So, but the idea is pretty much the same. Just the only thing changes log K become log CD, log A become log A2, and n log 2 over rho become n log 2 over 1 minus r squared. And this part is the same, okay? So with this equation, actually we're able to rewrite this equation, rewrite the equation for CD, okay? Okay. So let's see. What should we do in here? So your B, so our intercept equals to n log 2 over 1 r squared plus log CD plus log A2, okay? Because this part is your new intercept of B. Okay, so we take the CD to the left-hand side. Okay, so it can be easily derived the equation for the CD. I mean, E B minus n log 2 over r squared minus log A2, log A2. Okay, so that's actually how you calculate the CD, the coefficient for the Venturi using method 2. Okay, the equation is a little bit different. Okay, it's no more log A, because log A is the opening of the orifice, and A2 is the contraction, the area of the contraction for the Venturi meter. And instead of 2 over rho, it's a 1 over r squared for the Venturi. Okay, so I think that's pretty much it for the part A. Okay, the part A using method 1 and method 2. Okay, and for part 2, we're using a flow coefficient Kv instead of the CD of the Venturi section. Okay, so we can also formulate discharge for Venturi in form of a flow coefficient instead of CD. Okay, so let's see. Okay, so basically it means we don't use the CD anymore. Okay, we combine this part. We combine in a denominator 1 over r squared. We take it out with the CD and form a new coefficient we call K. Okay. Okay. So basically your KV is your original CD, and the part, the 1 over r squared, we just take it out. So we form the new KV. And we use method 1 and a method 2 to solve this KV. Okay, that's only for the Venturi section. Okay, that's for the Venturi meter. So using method 1 and a method 2, we're able to get the KVM1, which is from, okay, we denote the KVM1 means the KV calculated by method 1 and KVM2. Okay, so that's part 2. And calculate the theoretical discharge using the pressure drop and the flow coefficient, determining from the regression analysis. Do this both for the Venturi and Oliver's meters. Denote the computed discharge as QM1 and QM2 for each meters. Okay, that one is a straightforward too, right? Because you have already have all the information in here. Okay. And at the beginning, we use the measured Q to get the coefficient, the flow coefficient, or discharge correction coefficient. And right now, once we have the coefficient already, we can use our data and the coefficient to calculate a Q. Okay, that's our theoretical Q. And we can compare that Q to the measured Q to see if there is any difference. Okay, so I think this one is a straightforward too. Okay, and I think that's pretty much it for the analysis of data. Okay, please let me know if you still have any questions regarding the calculation. I think the calculation for lab 3 is the most complicated one. Yeah, you need to yeah, that's a lot of work. So hope you guys can finish it without any problem. Okay, thank you so much.